So we are still talking about the determination of the absorption tower, and this time let's start talking about a plate tower or a tray tower. And in a tray tower, the concept is more simple. However, the correlations used in calculating the height is a little bit more complicated. So in terms of concept, if you remember when we were starting chapter 3 and determining the number of stages required to achieve a certain level of purity or recovery, we had a major assumption assuming that the exit stream from each stage is going to be at equilibrium. And we know this assumption is not valid. We know that we can never reach equilibrium. Or actually we need an infinite time to reach equilibrium. So in this case, what you need to do is basically we need to see how far we are away from equilibrium, and this way we will be able to see the efficiency of each tray. The closer to equilibrium, the higher the efficiency of the tray. And basically, in general, the efficiency is basically, this is what shows. We have y local in minus yn local, which is the out, minus yn is equal to this out supposed to be equilibrium value minus yn plus 1. So the higher the value, that means we are getting to the equilibrium we desire. However, the situation is getting this value of y equilibrium for each single stage is quite problematic, and usually this is done by going to the lab and doing a pilot plant where we have a pilot absorption column where a sample of this outlet gas stream is basically collected. The composition is measured and compared to the actual equilibrium value. So instead of that, we will be using set of correlations to calculate the efficiency of the tower. Now keep in mind these correlations, they are not really very accurate. The source of errors basically can be up to 50% or even 80% sometimes. So whenever you are using these correlations, you have to be really very careful with the values obtained from these correlations. Typically speaking, the values of efficiency in an absorption tower can be between 60% to 80%. And to determine the actual efficiency of every plate, you really have to develop or construct a pilot absorption column to determine the actual efficiency of each of your trays. So if we would like to use the correlations, we have a simple diagram of different trays, and if we get a closer look at one of these trays, the efficiency of each tray depends on how close we are to equilibrium, as we said. And how close to equilibrium we can get, it depends on how good the mixing between the gas stream and the liquid stream, and for how long this contact is taking place. And as you can see across a single tray, if we look at this local point here, we will see that the contact between the gas and liquid will be shorter compared to, for example, somewhere at point here. So we will see that even across a single tray, the efficiency at this point, we would expect it to be different than the efficiency here, because we would expect that the mass transfer here is going to be different than the mass transfer rate at this point. Moreover, you would expect that the composition of the liquid, while it's moving across the column, is going to be different because it's going to absorb some of the gases. and therefore the mass transfer driving force is going to be different from one point to another. And therefore, in order to calculate the efficiency of the whole column, we have to start with a single point. And this single point efficiency. And this single point efficiency, this is what's called a local efficiency. Local efficiency is basically the mass transfer efficiency at a single point on top on a tray. And then we have to generalize this local efficiency to the whole tray. And this is what's going to be called the tray efficiency. And once we know the tray efficiency, or the efficiency, mass transfer efficiency of a single tray, now we have again to generalize this value of efficiency for the whole column. And therefore we will have the overall efficiency. So now we have three types of efficiencies. The local efficiency, which is the mass transfer efficiency at a specific location on a tray. And then we have to generalize this to the tray efficiency, which is going to be the average mass transfer efficiency across a single tray. And then again generalize this for the whole column, and this is going to be called the overall efficiency, and it's going to be the overall mass transfer coefficient for the entire tower. So we have three efficiencies. We start with the local, then the tray, then finally the overall efficiency. And once we calculate the overall tower efficiency, we can easily calculate the actual number of stages, because we know efficiency equal to theoretical divided by actual. Theoretical, we already know how to calculate the ideal number of stages from chapter 3. If we know the efficiency from here, we can easily calculate the actual number of stages required to achieve a certain level of purity. So let's start with the local, or calculating the local efficiency. And the local efficiency can be easily calculated using this simple correlation. And you can see how simple it is. It requires basically all your knowledge that you gained in this course. As you can see in here, it's basically the local efficiency is basically a function of Reynolds-Freud number, which can be calculated using density of the gas, V naught, which is, if you remember, the velocity of the gas stream through the holes, HL, calculated while calculating the pressure drop, viscosity of the gas, and phi E, which was basically, if you remember, capacity factor used to determine the diameter of the tray. Then we have again HL, which we know what it is, D naught, the whole diameter on a CV tray, AH over AA. AH is the total area of all the holes, and AA is the active area. And in here we have M, which is Henry's constant. We have Cg and Cl, concentration of the gas stream, concentration of the liquid stream at that specific point. So in general, concentration values can be calculated using density over molecular weight. So density of the gas over density of the liquid. Because the system is diluted system, and we can assume that the change in concentration and the change in concentration of the gas phase, concentration of the liquid phase will be very small, and therefore we can neglect it. So we can calculate the concentration of the gas and the concentration of the liquid stream at the bottom of the column, and that's going to be enough for every single tray. Then we have dG and dL. dGA is basically the diffusivity coefficient of the solute through the gas phase, and dL is the diffusivity coefficient of the solute through the liquid phase. And again, we have phi E, capacity factor, AH over AA. So all of these parameters were already calculated or determined during the calculation or determination of the diameter, which we did in chapter 4. So if you have already all of these in Excel format, in an Excel worksheet, you can easily now combine all of these parameters and calculate the local efficiency. Now, once we calculated the local efficiency, as I said, we need to generalize this value of efficiency for a tray, for a single tray. So we need to calculate the average efficiency across a single tray. And in here, we will have three different scenarios. The first scenario is basically we have both the gas streams and the liquid streams, they are perfectly mixed, and therefore the composition of the liquid stream is the same everywhere. The composition of the gas stream is the same everywhere. The second scenario is vapor stream is well mixed, however, the liquid stream is not. And the third scenario is basically neither vapor nor liquid streams, they are well mixed systems. So both vapor and liquid are partially mixed. They are not well mixed system, both of them. So the first scenario is both of them, they are well mixed. Second scenario, only vapor is well mixed. And the third scenario is neither of them is well mixed. So let's see when we can see these scenarios. The first scenario, which is basically both vapor and liquid phase are well mixed, we can see it in basically a small diameter tower, which is basically if the tower diameter from chapter 4 is less than 0.5 meter, then basically both streams will be well mixed streams, and therefore the local efficiency will be the same everywhere on top of that tray. And therefore, the tray efficiency, the average tray efficiency, will be equal to the local efficiency. Now we have to keep in mind, if you remember, if we have a tower diameter less than 0.5 meter, or actually even less than 0.6 meter, in this case, we are not supposed to use a tray tower column. We're supposed to use a packed bed column. So generally speaking, to see something, such scenario where we have a perfect mixing of both vapor and liquid phase is basically impossible. Even if we have a perfect mixing, then we are not supposed to use a tray tower. The second scenario and the third scenarios are basically based on the value of Bislett number, and we will talk more about it, and the value of H2 phi over T. And now if you remember, H2 phi is basically a parameter that we calculated when we were calculating the entrainment in chapter 4. And T is the tray spacing between the column. So what we need to do is, the first thing is we need to look at the value of H2 phi over T. If H2 phi over T is greater or equal to 1, then the system is going to be 100% both scenario number 3. Both vapor and liquid are partially mixed. So we calculate H2 phi over T, which is something actually we already calculated when we were calculating the value of entrainment. If it is more than 1, then we are in this scenario. If it is less than 1, then we have to check for Bislett number. If it is more than 50, then it is scenario 3. If it is less than 50, then it is scenario 2. So in order to calculate Bislett number, we need to use this correlation here. Again, this correlation is used for H2 phi over T less than 1, because if it is more than 1, we know we are already in this scenario. If it is less than 1, we have to calculate Bislett number to know in which scenario we are. So Bislett number of the gas phase equal to 4 volumetric flow rate of the gas phase. RW, if you remember, RW is the distance between the weir and the center of the tray. RW is the distance, how far the weir is from the center of the tray. AA is the active area. T is the tray spacing. H2 phi parameter related to entrainment. And we have DEG. And DEG is basically gas phase eddies diffusivity. So again, as you see, now we are combining all our knowledge during this semester to finalize the design of an absorption column. So DEG is the eddies diffusivity in the gas phase. And generally speaking, this value of eddies diffusivity in the gas stream is usually more or less a constant value, which is equal to 0.01 meters squared per second. So again, we check for this. First of all, scenario number 1 is out of the question. We will not see it because it takes place only for a diameter less than 0.5, and in that case we have to use packed bed anyway. Scenario number 2 or scenario number 3, first we need to check for H25 over T. If it is greater than 1, then it is scenario number 3. If it is less than 1, then we have to check for Peslett number. Peslett number less than 50, scenario number 2. More than 50, scenario number 3. And we can calculate Peslett number using this equation here. So we calculated Peslett number and it is less than 50, then it is scenario number 2. How we can generalize the local efficiency we calculated to the tray efficiency, and we can do that using this, again, this correlation. So the tray efficiency will be equal to 1 plus lambda local efficiency over n to the power of n minus 1 over lambda. The first thing I would like to say here, lambda, which we will see in the next slide, lambda is basically stripping factor, or basically 1 over capital A absorption factor. So lambda is the stripping factor. We have lambda, local efficiency, and n can be calculated using the Peslett number in the liquid phase, which basically can be calculated with similar equation to what we saw earlier, but now we are using the volumetric flow rate of the liquid stream, and it is diffusivity in the liquid phase, and this can be calculated using this equation. So it is diffusivity in the liquid stream will be equal to 0.1 times G H25 cube to the power of 0.5. So this is scenario number 2, how we can generalize the local efficiency to tray efficiency. Scenario number 3 is basically both vapor and liquid are partially mixed. So this is either because Peslett number greater than 50 or H25 over T is greater than 1. And in this case, basically, we can generalize the local efficiency to the tray efficiency in scenario number 3 using this very simple correlation. Now, if you look at this, basically, this is the equation in scenario number 2 multiplied by a little bit of the same parameters. Remember, lambda is mv over L, which is the 1 over the absorption factor, or basically it is the stripping factor. Again, n is Peslett number plus 2 over 2, and Peslett number of the liquid phase is equal to this equation. So now we calculated the local efficiency. We generalized the local efficiency to the tray efficiency. So tray efficiency is the average mass transfer efficiency across a single tray. And now we need to generalize this value in terms for the whole tower, or for the whole absorption tower. And in here, plus or that, in addition to considering the average efficiency of every tray, but also we need to consider the effect of entrainment. And if you remember, entrainment is basically liquid droplets are carried up by the gas stream. And whenever we have those liquids getting from one tray to another, to the top tray, it's going to disturb the system, and therefore it's going to reduce the efficiency of those trays. So therefore, the higher the entrainment value, the lower the efficiency we will get. So in this case, in order to calculate the overall efficiency, we need to use this correlation. So overall efficiency will be equal to the tray efficiency times 1 minus 0.8 local efficiency lambda, which is the stripping factor. So this is lambda to the power of 1.543, lambda to the power of 1.543 times E, which is the fractional entrainment, which we learned how we can calculate by the end of chapter 4, divided by M, and M, if you remember, is Henry's constant, or the equilibrium constant. Now, as you see here, in order to increase the overall efficiency, we need to decrease the value of entrainment. And if you go back and check on how we calculated the entrainment value or the fractional entrainment value, we will see that we need to reduce the gas velocity, we need to increase the tray spacing between the trays, and so on. And all of those you need to keep in mind that it's going to have design constraints as well as disadvantages. So you need to think about it that way. So basically that's it. Now we calculated the efficiencies. We need to see how we can use those values in order to calculate the plate tower height. So efficiency, we know that the physical definition of the efficiency is basically equal to theoretical number of stages over actual number of stages. Remember, theoretical number of stages, they are the same as ideal number of stages. So once we calculate the overall efficiency, now we can calculate the actual number of stages will be equal to theoretical number of stages divided by the overall efficiency. And once we know the actual number of stages, so it is easy. We have the number of stages, we have the spacing between them, so the height of the column will be equal to the actual number of stages multiplied by tray spacing. Now, remember, we have a space at the top, space at the bottom we need to consider. So the tower height will be equal to number of stages multiplied by the tray spacing plus top and bottom height. And in a tray tower, general rule of thumb is the top height equal to the bottom height equal to the tray spacing. So this is a general guideline. You don't have to stick on it. There are some considerations need to be taken into consideration. However, to simplify the situation for this level of design, we can say basically tower height will be equal to number of stages multiplied by tray spacing plus 2 tray spacings. The last thing that I would like to mention here, if you remember when we were calculating the ideal number of stages or theoretical number of stages, we were getting values, for example, 5.3 or 5.2. And at that level, we were saying we should not round it up to the next number of stages. Because this is only an ideal number of stages, we should not round it up. Now then, we calculated here the actual number of stages. So let's say now the actual number of stages is 10.3. In that case, now, because they are actual, they are real number of stages, we cannot have a 0.3 stage. So we will have to round this value up to the next level of stages. So 10.3 should be equal to 11 stages. So that's it basically in terms of the design or determination of plate tower height. Now, I would suggest that you build up on the example that you solved at the end of chapter 4, and you try to calculate the height of the tower that you already calculated the diameter, you already determined the tray design of that tower, and then calculate the efficiency, calculate the number of actual stages, and then the height of the column.